Well, welcome to our first webinar, and this is a fairly quick introduction to the cone penetration test. So a little bit about the history of the CPT. It was first developed back in the 1930s as a mechanical device in Holland, and they used it basically just to probe the soft sediments to find out where the sand layer was. And then in the early 1960s, it sort of evolved into an electric probe, and that's what it has stayed as since then. So it's been around for over 50 years as an electric device. And in the 70s, it became used extensively in the offshore industry and is now continued to be the primary in-situ test for offshore investigations. And since the 70s, lots of developments have occurred. Some of the main ones have been the addition of pore pressure measurements, and then more reliable cone designs, more reliable load cells and electronics. And then in the early 80s, geophones were added so that you could measure shear wave velocity. And then in the 80s and 90s, quite a few new sensors were added for environmental applications. And then also, since the 70s, a significant number of documented case histories have been published where CPT results have been used in case histories. And so our knowledge of how to use CPT results for geotechnical design applications has grown enormously. So the basic cone parameters are basically, there are two load cells. The first load cell measures the force on the tip, and when that's divided by the cross-sectional area, gives you the tip resistance in units of stress. And then there's a second load cell that measures the force of the soil as it rubs against the friction sleeve, and when that's divided by the surface area, gives you the sleeve friction in units of stress. And then there's a saturated porous element and a pressure transducer that measures the pore pressure. And that's typically located just behind the tip on the shoulder of the cone. So the cone will measure three things: tip, friction, and pore pressure, essentially continuously while the probe is pushed into the ground at a constant steady rate of 2 centimeters a second. So the primary applications of the CPT is, the first one is for stratigraphic profile. Since it does measure these three parameters continuously, you get an excellent detailed stratigraphic profile, and you can identify the materials present. You can also estimate a very wide range of geotechnical soil parameters, and then also you can do a lot of direct geotechnical design. When the device was first developed in Holland, the Dutch used it for pile design, and so pile design is certainly one of the most mature direct geotechnical design methods using the CPT. But others have been added. You can estimate the bearing capacity of shallow foundations, and you can estimate liquefaction resistance directly from CPT results. So when it comes to what level of sophistication is appropriate for a site investigation and analysis, this slide sort of summarizes the 4 key points, and essentially it's based around the precedent and local experience, how complex the design objectives are, how high a level of geotechnical risk exists, in other words, what are the hazards and how likely are the hazards to occur, and more importantly, what are the consequences if these hazards were to occur. And then the fourth one is the potential for cost savings. So if you have a project, typically a relatively small project that might have a lot of local experience, relatively simple design objectives, relatively low geotechnical risk, and a relatively low potential for cost savings, then often we use very simplified traditional methods that are often heavily weighted on empiricism. So a lot of simple empirical design methods. And they're perfectly adequate for these low risk projects. But for the larger projects where maybe precedent and local experience is rather poor, design objectives can be more complex, and the level of geotechnical risk is much higher, and the potential for cost savings is much higher, then often we use more advanced, complex analytical techniques as well as more complex site investigation, of which the CPT will be a part of that, but often it will involve additional in-situ testing and often additional high-quality sampling and high-quality lab testing. This flowchart sort of illustrates the process. So for low-risk projects, often a very simple site investigation involving in-situ tests. In the old days, that would have been the standard penetration test. Nowadays, it involves things like the CPT or the flat dilatometer. And then that's often linked to just small disturbed samples where you can do index testing. And then often those two are combined with simple empirical correlations for basic design. But for moderate risk projects, often a basic site investigation, but combined with maybe some additional in-situ testing. For example, if you had soft clays, you might do some field vein testing. If you had some very stiff soils, you might do some pre-bored pressure meter testing, some Maynard type pressure meter testing. You might also do some basic sampling, sort of Shelby tube sampling, not the highest quality, but with basic lab testing, and then link that results back to the in-situ testing. Undisturbed samples, Shelby tube samples often being the most popular. But for high-risk projects, often you'll do in-situ tests, and if the ground is suitable, tests such as the CPT to get a very good handle on the stratigraphy and variability of the ground, do preliminary estimates based on the CPT results, and if there are zones that are critical for the project, often a more detailed investigation that may involve additional in-situ testing, high-quality undisturbed samples, high-quality lab testing. But since the lab testing is slow and expensive, often the results of that lab testing is linked back to the in-situ testing so that the results can be extrapolated across the site. So CPT clearly plays a role all the way from low risk all the way to high risk projects. So what are the advantages of the CPT over traditional drilling and sampling? Well, it's relatively fast. It's pushed in at 2 centimeters a second, which is a little over a meter per minute, or 4 feet per minute. It's essentially continuous, although nowadays when it's digital data, it's near continuous. It's often digitized every few centimeters, so it's not strictly continuous, but it's close to being continuous. It's very repeatable and reliable, so if you get 2 different contractors out, you get essentially the same result. And of course, because of the speed and the amount of data you get, there's significant cost savings. So this is a slide that Paul Main has used, and I borrowed it from him, as an example comparing sort of conventional drilling and sampling, where if you want to get a lot of information about the ground, you often have to do a lot of different things, maybe standard penetration test, in addition to things like field vane and pressure meter, maybe cross-hole to get shear wave velocity, so that you can fully characterize the ground. Whereas nowadays with direct push technology, you can do CPT with pore pressure measurements, and if you add seismic, then you measure 5 things simultaneously while you push this probe in the ground. So you can measure tip, friction, pore pressure, shear wave velocity, and if you do dissipation tests, you can determine the time it takes for that dissipation to occur, often in terms of 50% of the dissipation, which is T50. So you can measure 5 things simultaneously with one test. Now, often the criticism of the CPT in some parts of the world is that you don't get a soil sample. And although that's true that you don't get a soil sample while you're doing the CPT, it is possible to move over and to push in a variety of very simple direct push samplers. Here's one illustrated, one that we use quite a bit. It's about the same size as a cone. It's essentially a couple of inches in diameter, about 50 millimeters in diameter. It looks just like a cone, except there's no electronics inside. And so when you've done the CPT, you get a very good detailed stratigraphic profile. And then depending on the project, what the project requirements are and what the ground is, you identify the layers in which you would like to verify the soil type, and then you move over approximately 3 feet or a meter, and then you push in one of these direct push samplers, and you go to the exact depth of the layer that you're most interested in, and you quickly take a small disturbed sample. It's only about 25 millimeters, 1 inch in diameter, by about 30 centimeters long, 12 inches long. So it's about the same size as an SPT sampler, and it's perfect for soil classification and index testing. And when you push the rods in to take the sampler, you don't have to push at 2 centimeters per second. You can push at whatever the speed of the hydraulics is capable of doing. And on the Gregg trucks, that is about 20 times faster. So you can take these samples very quickly. So rather than take samples every 1.5 meters or every 5 feet, you now take 1 or 2 samples at discrete intervals based on the soil stratigraphy and the project requirements. So you focus in on the layers that are most important. So there are many different types of pushing equipment. Here's a slide that illustrates a range of specialized CPT trucks. The big white one in the top left-hand corner is a Gregg truck, but they come in many different sizes and colors. And there are also specialized vehicles to push CPT under difficult ground conditions. Either in the lower left-hand corner you see essentially a swamp buggy, or modified pieces of equipment to get into difficult ground conditions. You can also push the CPT with a drill rig. This slide illustrates a small track-mounted auger rig, rig. It doesn't weigh very much. It only weighs about 5 tons. But you can push a CPT off the back. And the advantage of using an auger rig is you can actually install a flight of augers to anchor the rig down. So it's very quick and easy to anchor down, and then you just push the CPT with the drill rig. The advantage of pushing CPT and drill rigs with a drill rig in difficult ground conditions is you have the option, if you encounter a hard layer like a gravel layer or a very hard cemented layer, you have the option to pull the cone out and then go back down, drill through the hard layer, and then resume CPT afterwards. Of course, you also have the option to drill and take high-quality undisturbed samples. There's also various portable equipment. Here's an illustration of a small ram set that's designed to work inside buildings. It can be bolted to a concrete floor and gets the reaction from the concrete floor. It has a hydraulic power pack that can be up to 150 feet outside the building. And these portable ram sets can also be attached to any heavy piece of equipment to generate the reaction force. And one of the advantages that CPT has, of course, is improved safety using pushing devices. That there's no hammer, there's no rotating parts. You have the similar sort of safety precautions of any direct push equipment. The other advantage is you have no cuttings. And in California, if you are drilling on a site that has potentially contaminated soils, you have to dispose of the cuttings, and that adds a significant cost to drilling. And so with the CPT, you're just pushing this small diameter probe in. There are no cuttings coming to the surface. So obviously reduce cost and, of course, reduce contact of personnel with possible contaminated ground. And, of course, lower visibility and public exposure. You know, if you have one of these enclosed trucks, typically the public is unaware of what you're actually doing. This slide illustrates what the various probes look like. The original CPT that came out of Holland was 10 square centimeters in diameter. That's about 36.5 millimeters in diameter, about 1.5 inches in diameter. But most standards also now accept the slightly larger 15 square centimeter. And in fact, the 15 square centimeter is becoming more popular because it is a little bit more robust than the original 10 square centimeter. And also, it's a little bit larger than the push rods. Most push rods are 10 square centimeters, and so when you're pushing the traditional 10 square centimeter cone, you actually have to have a bump in the rods about 1 meter back from the cone that pushes the soil away from the rods to minimize the amount of rod friction that develops on the push rods. But when you push a 15 square centimeter cone, the probe is already larger than the rods, and so there's less rod friction. So it's actually easier to push the 15 square centimeter cone into most soils. Occasionally some people have developed larger probes, and this illustrates 40 square centimeter ones. They've tended not to be so popular. They were designed to push into gravelly soils. And at the other end of the spectrum there are these mini CPTs down as small as 2 square centimeters or 5 square centimeters, and they have become very popular for offshore work, for pipeline studies where you're not wanting to push very deep. Typically you're only pushing about 10 meters or 30 to 40 feet, but you require a much smaller reaction force to push these smaller probes. Now, over the years, a number of sensors have been added to the cones because they become completely electronic. Now they're digital cones, so it's much easier to add a variety of sensors. And as I commented, back in the 70s, pore pressure sensors were added, as well as inclination to check the verticality of the probe. And a lot of probes have 2 inclinometers in to check the verticality in both the X and the Y direction. And then in the 80s, geophones were added, where you could measure both shear wave velocity and P wave velocities. And then in the 90s, people had the idea of adding a little camera to actually look at the soil. That's become less popular because it can be pretty boring watching 8 hours of video of soil going past the cone. But in the 80s and 90s in the geoenvironmental industry, lots of sensors got developed and added to the cone. In the early days, simple things like pH, temperature, electrical resistivity or conductivity, but more recently, more sophisticated probes like laser-induced fluorescence to detect hydrocarbons. We won't talk about those geoenvironmental sensors in this webinar. We'll cover that in a subsequent webinar. Now, the only correction you need to be aware of that the cone requires is the fact that because the sleeve is behind the cone and therefore there's a reduction in the the load cell to fit that sleeve around, because the sleeve has the same diameter as the tip. Then when the cone is lowered in water, the water pressure acts on that shoulder at the back of the cone. And so in terms of the water pressure, the net area of the cone is less than its gross area. And so about 30 years ago, this was identified, and so most cone data, the measured QC is corrected to a total stress, a QT, and that correction is where you add on a portion of the water pressure that acts on that shoulder. And most cones have a net area ratio somewhere between 0.6 and 0.8, and so you're adding on a correction of about 0.2 to 0.4 of the water pressure, which in sands is almost an insignificant correction. So in the literature, quite often you'll see QC talked about for sands, because there's essentially no difference between QT and QC in sands, because QC is a very big number, hundreds of atmosphere, where the water pressure is essentially free draining, so it's hydrostatic, it's a relatively small number. But in soft clays, QC can be a very small number, maybe just a few atmospheres of stress, and the water pressure can be a significant portion of that, because when you push the cone into soft clays, you generate large excess pore pressures, and so U2, that water pressure just behind the shoulder, can be quite large, and so this correction can actually be quite significant, in the order of 10 or 15% correction. That's about the only correction that people need to be aware of. Most contractors make that correction, so quite often when you're presented the data, you'll be presented the raw data, QC, FS, and U, and then the corrected data of QT, FS, and U. When it comes to interpretation, there's a wide range of interpretation available. The most common, of course, is to identify soil type, and we'll talk briefly about that. The state of the soil, either relative density or state parameter for sands, or stress history, OCR, for clays. Strength parameter, peak friction angle in sands, or the undrained strength in clays. The stiffness or compressibility, either Young's modulus, shear modulus, or one-dimensional constrained modulus for compressibility, and then also consolidation and permeability parameters, the coefficient of consolidation or the hydraulic conductivity or permeability. I'll just touch on some of the main ones, the first one being soil type. And the important thing to notice here is that traditional classifications that we use based on samples are based on grain size and Atterberg limits. The CPT doesn't respond directly to grain size and Atterberg limits. Instead, it responds to the strength, the stiffness, and compressibility of the soil. So it responds to the behavior, the mechanical behavior of the soil. So these, quote, classification charts are really soil behavior type charts. We use the traditional terms of sand, silt, and clay because that's what we're used to with classification, but really we're saying that the soil is behaving like a sand or it's behaving like a clay. And the early charts that were used were charts that you see on this slide, which typically have cone resistance in atmospheres of pressure on the vertical axis, and then friction ratio on the horizontal axis. And friction ratio is the ratio of the sleeve friction to the tip resistance in percent. So it's the relative friction. And what we know is that sandy soils tend to have high tip resistance and low friction ratio, and clays tend to have low tip resistance and high friction ratio. And soils in between tend to fit in that mixed zone. But it's important to remember that there is a difference between the soil behavior type and traditional classification based on samples. Now these charts were developed close to 30 years ago now. And they're still very popular, and one of the reasons they are popular is they just require the raw measured data with the CPT. So you can estimate soil type just based on the tip and friction that you measure in the field. So nowadays with computer data acquisition systems, this can be done in real time. So while you're pushing the cone, the data acquisition system can actually give you an indication of what type of soil you're in. But it was recognized that these charts had limitations in the sense of they generally applied to relatively shallow CPT soundings, typically in the order of about 10 to 15 meters, 30 to 50 feet. But nowadays with bigger pushing equipment, we push CPTs much deeper. It's not unusual to push a CPT 50, 60 meters or several hundred feet. And when you go deeper, of course, the overburden pressure gets larger, so the tip resistance gets larger, and these non-normalized charts tend not to work so well. So it was about 20 years ago that we switched to normalized charts, and this is just an illustration of a typical presentation. I'll show you the normalized chart in a second. So this is a sort of a typical example of a presentation of CPT where you've got a profile of tip resistance, friction ratio, pore pressure, and then the computer output of soil behavior type. Now, I mentioned about the normalized chart, so about 20 years ago the charts got updated, and recognizing that we really should normalize particularly the cone tip resistance by the vertical effective overburden pressure. So these normalized charts have become more popular and they are more reliable, and so they are normalized tip resistance against normalized friction ratio. And the normalized tip resistance is just basically the net cone resistance, so QT minus the total overburden divided by the effective overburden. So it's normalizing out the effective overburden pressure. And then you can see that the normalized friction ratio is the sleeve friction divided by the net cone resistance in percent. Now you notice it's now put onto a log scale, and that's because sands tend to have friction ratios less than 1%, and so by putting it onto a log scale it sort of expands the sand region so that you can see the data a little bit better. So now they tend to be on log scales, and again sands tend to have high tip resistance and low friction ratio, clays low tip resistance and high friction ratio. Now when those charts were first developed, several researchers identified that the boundaries between the zones were roughly concentric circles. And so Jeffries and Davies about almost 20 years ago came up with the idea that you could combine these normalized parameters of Q and F to come up with a single parameter that they referred to as the soil behavior type index, IC, which is essentially just the radius of these concentric circles. So when IC is small, you're up in the sand region, and when IC is large, you're down in the clay region. And so this single number could identify soil behavior type. And it essentially varies from a value of 1 up in the top left-hand corner to about 4 in the lower right-hand corner. So this single parameter could be used as an index of soil type, and that's turned out to be a very powerful concept because people have used this soil behavior type index as a way of modifying some of the correlations that vary as a function of soil type. So as soil type varies, then the soil behavior type index IC will vary, and so you can modify correlations based on that single parameter that combines the two measurements from the CPT. This next slide is just to illustrate the repeatability of the test. This is 2 soundings, they're to 15 meters, and you can see excellent repeatability on the tip resistance, pretty good repeatability on the friction ratio. The pore pressure is not bad, although what you do tend to find is for onshore CPTs, the repeatability of the pore pressure is not always perfect, and that's partly because of the complexities of potentially losing saturation of the pore pressure sensor. In this particular case, although the water table is just a couple of meters down, the two are responding quite well, but by the time it gets down to about 7.5 meters, there's a slightly dense layer there that caused the red sounding to just go slightly negative, and probably a few air bubbles came out of solution, and so the red sounding was a little sluggish from about 8 meters to 9 meters due to those small air bubbles that desaturated the porous element. But then you can see it became saturated again and started to respond quite rapidly. So what we do tend to find is that the pore pressure data tends to be used in a more qualitative sense for onshore CPT, partly because of the difficulty of ensuring whether or not that sensor maintains saturation. In the offshore industry, pore pressure is used a lot because they can essentially guarantee that the sensor remains saturated if you're in deep water. And also, if you're in very soft sediments where the soils are very soft, excess pore pressures are very large, and the water table is very close to the ground surface, the pore pressure also becomes a very reliable parameter. So there are many theoretical solutions for CPT. One of the nice things about it is that it is amenable to theoretical solutions, and over the years the theories have evolved. In the early days they were sort of rather simplistic bearing capacity theories, but then they've become more complex. Cavity expansion tends to be the more popular one. It's not perfectly correct, but it does capture a lot of the basic elements and therefore continues to be very popular. And nowadays there are a number of sort of combined theories, many of them that involve cavity expansion with some sort of solution to try and get closer to the real result. However, the challenge with all the theories is that you need major assumptions on the geometry and boundary conditions of the cone because it's got quite a sharp point and a sharp shoulder. Soil behavior is very complex, and drainage conditions can be quite complex too. So real soil behavior is very complicated. So what we do tend to find is that the semi-empirical correlations still tend to dominate, but they're strongly supported by theory. So the theory often has come up with a form of a solution, and then people have gone out in the field and actually collected real data with real soils and then sort of modified the constants in the form of the correlation to come up with semi-empirical correlations. So although we do tend to use empirical correlations, they are well supported by theory. So this little slide is sort of a schematic of the loading around the soil, and so it illustrates a sort of a generic stress-strain curve of the soil, and it illustrates elements of soil around the cone while the cone's being pushed. And you can see that elements of soil that are a long way from the cone are essentially loaded very little, and they're still essentially elastic. But then as you get closer to the cone, the soil begins to reach failure, and the soil essentially becomes plastic. And then when you get very close to the cone, the strains are very high, and you're essentially remolding the soil. And so the tip resistance responds to some cumulative effect of all of the soil around. And so the tip resistance is a closer measure of the peak strength of the soil, whereas the sleeve friction, because the soil that's passing the sleeve is essentially fully remolded, quite often the sleeve friction can be assumed to be equal to the remolded strength of the soil. And of course you can see that the pore pressure responds only to the soil in contact just behind that shoulder. Now, you saw from that schematic that you tend to have a zone of influence of the cone. The cone tends to sense both ahead and behind. And so when you're pushing the cone through interlayered soil, so if you're in a very soft clay and you start to push into a dense sand, the tip resistance will start to rapidly rise up to the true value within the sand, but it does take a certain distance before the cone no longer senses that soft clay above. And from this little diagram, this is a theoretical solution, but it's supported by both observations in the laboratory and in the field. It illustrates that in this particular case, if you had a very soft clay overlaying a very dense sand, you actually have to push a standard 10 square centimeter cone about 1/3 of a meter, or about 1 foot, into the sand before it starts reading its true value in the sand. Now, of course, if the sand layer is not very thick, these dashed lines illustrate that if the sand layer was maybe 1 meter thick, it would reach its true value and then begin to drop back off into the clay layer. And of course, as the sand layer gets progressively thinner, it will show a spike in the sand layer, but will quickly drop back off as it feels the clay ahead. And you can see that when the sand layer is less than 1 meter thick, then the peak that you measure in the sand layer may not truly represent the density of that thin sand layer. So we tend to underestimate how dense, thin, dense sand layers are in soft clay layers. And you can see that this transition zone, because we collect essentially continuous digital data, then some of the data points in this transition can be misinterpreted. So that red zone is a transition zone where we may just tend to underestimate how dense that sand is. Now that becomes quite important in some interpretations. For example, in liquefaction analysis, that becomes quite critical because we tend to predict that the upper portions of these sand layers appear to liquefy. So in highly interbedded deposits, both the upper zone and the lower zone of each sand layer looks like it could liquefy, which is not strictly true. It's simply where the cone is in a transition from one soil to the other. So how useful is the CPT for deriving soil parameters? Here's a table that illustrates a wide range of parameters that you can estimate in sort of sands and clay. And 1 rating is highly reliable, 2 is moderate to high, and 3 is moderate. 5 is of low reliability. And you can see that there's pretty good reliability. CPT is very good at estimating the strength of the soil and pretty good at the in-situ state, stress history and relative density. Traditionally, it's not been very good at deformation characteristics, the stiffness or compressibility. But nowadays, by including seismic measurements that are a direct measure of stiffness, that's improved enormously, and I'll touch on that briefly in a few minutes. So I just want to talk about some of the major interpretations, and certainly since the CPT has historically been used primarily in softer soils, things like clays, so I'll talk briefly about OCR, stress history in clays, and undrained strength, just to give you an illustration of some of the interpretations. So there have been a number of theoretical solutions, most based on cavity expansion and critical state soil mechanics, and there are a number of different relationships that link CPT data to OCR, the over-consolidation ratio. The most popular is basically the normalized cone resistance, and that's why those normalized soil behavior type charts became so popular, because there is a direct link to the OCR of fine-grained soils. And so Paul Main put together a lot of data. This is just an illustration of the OCR on the vertical axis with the normalized cone resistance on the horizontal, and you see a lot of data. And Paul has suggested a sort of a generalized average relationship that says the OCR is essentially just 0.33 of the normalized cone resistance. In other words, the normalized cone resistance divided by about 3 would give you an estimate of the OCR. Now, based on theory and high-quality block samples, the relationship is a little bit different. It's sort of 0.25 times the normalized cone resistance to the power of about 1.25, and that's the red line. And you can see that for a relatively low OCR, there is almost no difference between the sort of the more correct version and the simplified version. But when you get into high OCRs, the more correct one gives a slightly better correlation. Now, when it comes to the undrained strength of clays, one of the challenges is the realization that there's no unique value of undrained strength. It is a function of direction of loading. And so when people have tried to estimate the undrained strength of clays, the key is to realize which one are you trying to link to. And the form of the relationship is essentially that the undrained strength is the net cone resistance divided by some constant. And theory says that that constant varies from about 10 to 16. With about sort of 14 or 15 being the norm, and then that constant tends to decrease with increasing sensitivity and tends to go up a little bit with increasing OCR or plasticity index. And in very soft clays, you can actually estimate the undrained strength from the excess pore pressure, and that's popular in very soft sediments and in the offshore industry. Give you a sense of what these numbers work out. Professor Chuck Ladd spent most of his career studying the undrained strength of soft clays, and he came up with this approach, often referred to as the Sept approach, which can be simplified by this relationship that says the undrained strength ratio on average, for the average strength, is roughly about 0.22 times the OCR to an exponent of about 0.8. And if you plug in that relationship that links OCR to normalized cone resistance, it actually kicks out that NKT should be about 14. And then recently a number of research, this one is from the University of Western Australia combined with the Norwegian Geotechnical Institute, where they went to a number of sites and they took very high quality block samples, did very sophisticated lab testing, determined what the average undrained strength was, looked at the cone factor, and found that it varied from about 11.5 to 15.5 with an average of about 14. So in general, an NKT of about 14 works about right for undrained strength. One of the nice things about the CPT nowadays is we do measure pore pressure, and so you can determine where the water table is. And this little diagram illustrates that when you're pushing the cone, you develop excess pore pressures, particularly in soft clays. And if you stop and let them dissipate, they'll eventually dissipate to equilibrium. Now, of course, if you're pushing in a clean sand, the permeability is so high that the excess pore pressures dissipate essentially while you're pushing. So you can actually measure the equilibrium piezometric profile while you're pushing the cone. And if the groundwater conditions are hydrostatic, you'll actually measure the hydrostatic groundwater conditions while you're pushing the cone in these clean sands. But in soft clays, you can generate large excess pore pressures. In very soft, sensitive clays, you can generate very large excess pore pressures. And then when you stop, they will dissipate, and the rate of dissipation is controlled by the coefficient of consolidation and permeability. And so you can record this dissipation test, and this next slide illustrates an example. And in theory, one way of looking at it is the excess pore pressure against the log of time. And you can see in this example as the pore pressures dissipate. And since it's logarithmic, it takes a long time to possibly dissipate to 100%. And so practice has shown that if you actually stop at about 50% of the dissipation, that T50 can be used to estimate the coefficient of consolidation and the permeability. In this particular example, it illustrates that T50 is about 7 minutes. And there's a theoretical solution that links the theoretical time with the measured time to calculate the coefficient of consolidation. And notice it's the coefficient of consolidation in the horizontal direction because primarily the dissipation is occurring in the horizontal direction around the cone. Now this example is in a soft clay where you get large excess pore pressures and they dissipate sort of down towards equilibrium. But in some soils, particularly stiffer clays, you can get this response where the pore pressures initially rise before they drop to equilibrium. And the initial rise is the fact that in stiffer clays they tend to be dilate in shear, so you can get quite low pore pressures behind the cone and very high pore pressures on the face of the cone. And so when you initially stop, there's some local redistribution before it starts to radially dissipate, radially, horizontally. And so people have developed sort of simplified relationships based on theory that link the coefficient of consolidation against this T50. And the chart on the left shows one we put together. The solid lines is the theory, and the dots were data collected from around the world, and they fit the theory pretty well. There's a few dots that are better off lower down, and those are typically stiff, fissured, highly plastic clays where the fissuring affected the results. And the little chart on the right shows that in general, the coefficient of consolidation estimated from dissipation tests generally agree reasonably well with those values from high-quality lab testing. Excuse me. And this chart illustrates how you can go the next step and estimate the permeability or coefficient of consolidation, hydraulic conductivity from the T50. Here the complication is that the permeability is a function both of the coefficient of consolidation and the stiffness of the soil, represented by the one-dimensional constrained modulus. And so the relationship's a little bit more complicated. So you've got lines that represent varying stiffness of the soil, and it's influenced by the effective overburden pressure. But in general, you can make reasonable estimates, at least to within an order of magnitude, of the permeability from dissipation tests. We'll go into these issues in more detail in subsequent seminars, but I'm just doing a quick overview to give you a sense of what's possible. So you can estimate flow characteristics from piezo cone data. There are some uncertainties. The theory is not perfect. There are lots of complexities of real soil conditions, but it does give you a very quick approximate estimate of the flow characteristics in fine-grained soils. And because you can do these tests quite frequently and quite quickly, they become quite a powerful way to estimate the variability of the ground. Now, as I commented earlier, in the 80s, geophones were added to the cones so that we could measure shear wave velocity. And the attraction for measuring the shear wave velocity is that's a direct measurement of the shear stiffness. So small strain elastic wave theory says that the small strain shear stiffness is the shear wave velocity squared times the mass density. And the mass density is just the unit weight divided by gravity. So by measuring shear wave velocity, you get a direct measure of the stiffness of the ground. So, we commented earlier that CPT is very good at estimating the strength of the soil, the stratigraphy, and if you measure shear wave velocity, you get a very good estimate of the stiffness of the soil. This is how the test is done. There's a geophone inside the cone, and so at a given depth you stop, and you have usually a horizontal beam on the ground surface. You hit that beam, you generate a shear wave that travels down to the cone, you pick up its arrival, and if you hit the beam on the other end, you get a similar wave except it's polarized the other way around, so you get a reverse sort of wave trace of the arrival time. And then when you continue to push the cone, if you then stop again 1 meter deeper and repeat the test, you can then determine the interval of time it takes for that shear wave velocity to travel that 1 meter. So that means you can end up getting a profile of the tip, friction, and pore pressure, plus you get this shear wave velocity at least averaged out every meter down the profile. So a very powerful technique, one that we'll talk about in more detail in subsequent webinars. One of the powerful things about the Seismic CPT is because it's a combination of measuring the small strain stiffness and the large strain strength of the soil, it gives you the potential to identify unusual soils like cemented or very old soils that are quite difficult to identify using traditional techniques. And we'll go into that in more detail in subsequent webinars. And likewise, you can do settlement calculations using that small strain stiffness, and we'll go into that in more detail in subsequent talks. So when it comes to geotechnical design, there's two sort of basic approaches. On the right-hand side is in a way the traditional indirect approach where you can interpret the in-situ test to get a geotechnical parameter and then put that into some analysis to do design. Or on the left-hand side, you've got the direct approach, which is you take the CPT data and go directly to design. And the most common example of that is pile design, where the Dutch realized very early that you could take CPT data and directly go to pile design based on CPT data without going to an intermediary step of estimating a geotechnical parameter. And that's become more popular. You can estimate bearing capacity of shallow foundations, and you can do things like liquefaction analysis. So how good is it on these design methods? This is a little table that sort of tries to illustrate that. And it says basically for things like pile design, it's very good. Bearing capacity is pretty good. Settlement, traditionally not so good, although recently correlations have been improved, and particularly with measurement of shear wave velocity, they're getting better. And then things like compaction control, quality assurance for ground improvement, and for liquefaction analysis, pretty good. So in summary, the CPT is a pretty fast test. 2 centimeters a second, roughly a meter a minute. You can do a 30-meter sounding in and out in less than an hour. It's pretty reliable. It's essentially operator independent. You get essentially the same result if you move over and repeat the test, or if you bring in a different contractor. Very cost effective because it is fast, particularly if it's locally available. And you can estimate the soil profile. You can get a wide range of geotechnical parameters. Of course, you can estimate the groundwater conditions, and not just where the groundwater table is, but actually determine the piezometric profile and determine whether or not you have artesian pressure and so on. And of course, you can do preliminary geotechnical design. And of course, also there are sensors for environmental purposes that we'll talk about in a subsequent presentation. And it's suitable for a wide range of soils, except of course very dense gravels and hard rock. Dense gravels and hard rock, you're going to hit refusal. You're not going to be able to push in those types of soils. Fortunately, though, is that humans tend to live in cities that tend to be on close to rivers or coastal areas or lakes, and so the soils tend to be relatively soft where a lot of people tend to live. So the CPT tends to have pretty wide application in many parts of the world. Now, because it's digital data, over the years, many software programs have been developed which make presentation and interpretation of CPT data easier. About 5 years ago, I got involved in assisting with software development, and we developed a software program called CPT, and it's sold by a small company in Greece. I'm just going to illustrate it. So Gregg actually sponsored in the development of this software. We don't get any return from the sales. I don't get any return from the sale of this software. We just wanted to see good CPT interpretation software easily available, and the key is because we sponsored in the development, the software program sells very inexpensively. It sells for less than $250 or less than 200 euros. So it's inexpensive and very powerful. And what it allows you to do, it allows you to look at the data, load the data in very easily. Here's an example profile of the basic data, and you can see you've got tip resistance, friction ratio, pore pressure, and then you've got this soil behavior type index, IC, and it's color-coded. The blue is clays and the brown is sand. And then you've got the traditional soil behavior type with words and color coding. And then you can look at normalized data, once you've decided where the water table is and what the phreatic piezometric groundwater conditions are. And then there's you can also look at the data on the soil behavior type charts, both non-normalized and normalized, and the software allows you to actually interrogate the points and know what depth they're from. And then you get a range of plots of various parameters. Here it sort of illustrates the estimated permeability from soil behavior type, the equivalent SPTN value, Young's modulus, relative density and friction angle in the sands, and then this other one is sort of the one-dimensional constraint modulus, the small strain shear modulus, and then the undrained strength. The black line is the peak strength, the red line is the remolded strength, and then the next one is the undrained strength ratio, and then the final one is the OCR. And there's also a third tag that talks about sensitivity and shear wave velocity. So I know that was a very quick overview, just to give you an introduction of what the CPT does and what it's capable of. In subsequent webinars, we'll go into each of these topics in a little bit more detail and won't whiz by it so quickly, so we'll be able to cover it a little bit more detail. Now, Kelly's handed over some of the questions, and I think the first question is, how reliable is the CPT in soils such as clay till or peat and other soil conditions? Arid conditions, yes. So clay tills. Now, when you talk about glacial soils, often they're very complex. It depends on the geology. Some clay tills are very clay-rich and rather weak. Other clay tills can have a lot of gravels and boulders in. And obviously, if you've got a lot of gravels and boulders, the CPT is going to be difficult because every time you hit a boulder, you're going to hit refusal and get stuck. If the boulders are rather isolated, then people have had success by, of course, pushing the CPT. When you hit a boulder, you just stop, move over, and try again, and hope that you go past the boulder. But certainly in the weaker clay-rich clay tills, then the CPT works quite well. You know, it's just basically a stiff clay, and the CPT results, you know, will tell you exactly how variable the soils are and give you good estimates of how strong the clays are. Now, when it comes to peat, peat likewise is highly variable. You know, organic soils vary enormously from one end of the spectrum essentially being organic clays to the other end of the spectrum essentially being very fibrous peats. In organic clays, they tend to show up in the CPT as just being very soft compressible clays with very low tip resistance and often quite high friction ratio because they're essentially clays, but they're soft and compressible due to their organic content. At the other end of the spectrum, when you get fibrous peat, if it's a truly fibrous peat, it's essentially just fibers in water. And so when you push the cone into those soils, those materials, you get very low tip resistance because you're essentially just pushing in water. You get essentially no excess pore pressure because you're just pushing in water, and so you essentially measure the hydrostatic water conditions. So you get very low tip resistance, usually very low sleeve friction, so friction ratio is very low, and of course you essentially get hydrostatic water conditions. So often fibrous peats show up as you know, free draining, but yet extremely low tip resistance and low friction ratios. And then, of course, other peats will fall anywhere in between those. So, you know, at one end I said the fibrous peats had very low friction ratio, and organic clays could have very high friction ratio. So obviously, depending on what peat you have, it can fall anywhere between those. But typically, it shows up as being very low tip resistance and often plotting very low on the charts as a warning it's a very soft material. And then depending on how much clay it's got in or how much fiber is how much excess pore pressure you get. If it's fibrous, no excess pore pressure. If it's clay, you get lots of excess pore pressure. In arid soil conditions, of course, obviously, pore pressure plays much less of a role because the soil is dry, and so the pore pressures generally become less meaningful because they essentially become unsaturated and measure maybe slightly negative water pressures. So everything's focused on the tip and sleeve. And in arid soil conditions, often the soils can be quite stiff, and so you often get very high tip resistances. Gregg has done quite a bit of CPT in the deserts of Nevada, and there, you know, the water table is often very low. The soils are often very sandy and silty. They're often very dense. You get very high tip resistances, and sometimes the cone can get very hot. And most cones now are temperature compensated to try and cope with temperature variations. But in extreme conditions, in very arid conditions, the cones can get very hot, and sometimes too hot to actually touch when you pull them out. So it's important to make sure you're using a cone that is fully temperature compensated and can cope with those high temperatures. But other than that, the cone data works just fine. It basically says, yes, we're dealing with a dry material and it's often very dense. One of the other questions was how far away from the auger or anchors or borehole should the CPT be done? And that's a good question because although when we talk about normalizing the cone data, we use the vertical effective stress. And the reason we do that is simply because we should really be using the horizontal or mean effective stress, but we don't know what the horizontal stress is most of the time. So we use the vertical effective stress as a proxy for the mean over horizontal effective stress. But because the cone is influenced by horizontal effective stress, then if you have a borehole nearby where there's stress relief, and so the horizontal stresses are dropped because of an adjacent borehole, that will have a significant effect on the CPT. So the typical rule of thumb is don't push the CPT too close to a previous open borehole. Now the advice is if you're going to do a CPT and an adjacent borehole is to do the CPT first, get the stratigraphy, and then do a borehole close to the CPT. Then of course the borehole is not influenced by the CPT because you're typically just taking samples. So do the CPT first followed by the borehole. But if the borehole has been done first, then typically the guideline is to move, often the rule is anywhere from 10 to 20 diameters of the borehole away. So if it's a typical 4-inch diameter hole or a 100-millimeter diameter hole, then typically you need to move at least 1 meter or 3 feet away from that borehole to ensure that you're not being influenced. Same for anchors. If you've installed augers to anchor with, you can be influenced by the result. So typically what happens is quite often if you're going to push with a drill rig that needs to be anchored and you're concerned about this because the anchors might be quite close, then what you can do is you can push the upper couple of meters without anchors and then install the anchor in those upper couple of meters and then continue on pushing. So that avoids any potential conflict between the two. And so either make sure that they're 10 to 20 diameters away, diameters of the auger, or push the cone first before you install the anchors. Okay, another question. Pore pressure in offshore, tidal areas and large tides. Now, when you're pushing the CPT offshore, the good news is that the pressure sensor is typically guaranteed to be saturated because it's below the water all the time. The complication can be is that you've got changing water conditions. So what the offshore industry typically does is reference everything to mudline or the sea floor. So what the offshore industry does is they lower the cone down to the mudline and then they take the zero load reading or the baseline reading at the mudline and then start everything from that. The reason for doing that is the effective stress in this soil is unaffected by the depth of water. So even though the water level may be going up and down, it's not influencing the effective stress in the ground at the mudline. So if everything is referenced to the mudline, then it's relatively, the tip resistance becomes independent of the water conditions. And likewise, when you reference out the water pressure, you're sort of removing most of it, not all of it, of course. Obviously, if you have very large tidal changes during the CPT, so let's say the tide is very low and you've got a relatively shallow depth of water at the beginning of the sounding, and of course you've zeroed that out of the mudline. If of course the water level starts to increase a large amount, then the pore pressure measurements during the cone are going to be influenced by that change, and you do need to track the time. And a lot of data acquisition systems do keep track of time, and so you can link that to the tidal variations, and you do have to account for it in the pore pressure. One of the other questions, the significance of the cross-correlation between QC and FS, should it be filtered? And they're referencing the software where it shows you this cross-correlation between QC and FS. And what that does is that when you're pushing the cone, the tip is in front of the sleeve, and so they're physically offset, and they're, the distance from the center of the tip to the center of the sleeve is nominally about 10 centimeters. So imagine if you're collecting data every, say, 5 centimeters, then it takes 2 data readings before the sleeve is where the tip used to be. And so a lot of data acquisition systems don't work strictly on a time basis, they work on a depth basis. And so what they do is they line up the tip and sleeve at the same depth, not at the same time. And so, if you're taking data every 5 centimeters, they shift the data by 2 readings so that the sleeve is now at the same depth as the tip. Now, not all data acquisition systems do that, and so the software CPT shows you a little cross-correlation to sort of say how well does the tip and sleeve match. And of course, if you get a nice bell curve and it matches at 0, it says that they are in fact nicely matched already. But if they're off a little bit, you have the option to sort of realign them. Now, of course, it doesn't always work that way because the tip, of course, senses ahead and behind. And so the tip is sensing soil ahead and behind, not constantly right where the tip is. And so there actually isn't a constant offset to match the tip and sleeve perfectly. And so people have played around with changing this offset. But over the years it's shown that just the physical offset seems to give a pretty good answer, that the results don't change significantly if you were to switch that. So whether or not you put that filter on or off typically doesn't change the result very much. Another question, what's the NKT value do you recommend for desiccated clay? So this question is related to if I want to estimate the undrained strength in a desiccated clay, what cone factor NKT do I use? And I sort of commented that in general it's around 14. It tends to go down with increasing sensitivity and go up with increasing OCR. And so of course desiccated clays are essentially over-consolidated clays where the desiccation has created an apparent over-consolidation due to desiccation. So the NKT tends to go up as you get more desiccated. So instead of 14 or 15, it tends to sort of nudge up towards 18 and sometimes as high as 20, depending on the desiccation. And also it's a function if the desiccation is quite severe and actually has created fissures and cracks in the clay, then that complicates life as well because the cone is relatively small and these cracks could be rather widely spaced, and so the undrained strength that you may need for your design may really be a sort of a large-scale undrained strength that is in fact influenced by these fissures. And so, research in stiff fissured clays in the UK have shown that NKT can actually go as high as 30 in these stiff fissured clays to account for the influence that fissuring has on the sort of global peak strength of these stiff fissured clays. Now another question, how sensitive is the data to the operators? Can an inexperienced operator screw it up? Well, that's a good question. I mean, the advantage of the CPT over traditional drilling and SPT is, of course, the standard penetration test is very operator dependent. Depends on the hammer anvil system. It's well documented that it's very operator dependent. Where the CPT, of course, is essentially independent of the operator. The load cells don't really know which operator is pushing the button on the surface. So it essentially is operator independent, and most commercial systems tend to be somewhat foolproof, but they're never 100% foolproof. It is possible for an operator to screw it up. Usually if they screw it up, it's obvious because the data is so vastly strange that there's obviously something completely wrong. But as long as they're following the recommended procedure from the manufacturer, as well as the standard, and ASTM standard, as do most national standards, they require that the zero load readings be taken at the start and end of every sounding. And so if you're unsure, what you can do as a user is ask the contractor to provide you with those zero load readings, sometimes referred to as the baseline readings, that should be taken at the start and end of every sounding. And so by monitoring those zero load reading, you can determine how stable the equipment is, whether or not there's any zero load drift, possibly due to slight temperature variations or damage to the cone. And so a good test of the reliability of the data is to simply ask for those zero load baseline readings, both at the start and end of every sounding, and the contractor should record those and put them into file. And so if you monitor those readings during a project, they should remain pretty stable. It shows that the cone is working well and has not been damaged. If there is a sudden shift, it means that maybe the cone has become damaged and you need to take that one out of service and put a different one in service and send the damaged one off to be recalibrated and checked. Another question is how accurate are settlement values in the software CPT? That's also a good question. Settlement calculations in general are not that accurate. I mean, there's lots of papers written that estimating settlements under various load conditions, particularly in sandy soils, is not that reliable. But CPT has embedded in it the more recent correlations, which do tend to be better than the older ones. They're not going to be perfect, and so what we tend to recommend is that if you're using CPT for the first time in a sort of certain geologic region, then estimate the settlement from the CPT, but then follow it up with alternative methods, as well as possibly, if you can, monitoring the settlement to see how well it did, and then over time adjusting how the program does in relation to your local soils. But certainly in general it does reasonably well. It tends to be slightly on the conservative side, but may need a little bit of adjustment based on your local conditions. Another question about liquefaction based on shear wave velocity. We'll certainly do one or two webinars in the future about liquefaction. It's a big, complex topic, but I think this question is basically saying how well is shear wave velocity for liquefaction. The typical answer is, yeah. In fact, if you can get your hands on the NSEER report, which was a paper by 20 authors, the lead author being Professor Yaud. It was in ASCE in 2001, and that sort of gives the NSEER recommendations that cover both the SPT, the CPT, and shear wave velocity. And so you'll see it covered there. Last little comment, OCR estimated by CPT compared to lab results. We quite often get questions where people will say, well, I estimated parameters from the CPT, but they don't agree with samples. And often the reason for that is often sample disturbance. That traditionally we go out and we take pretty basic samples using a Shelby tube. And a Shelby tube in general is not the most perfect sampler. It often has a rather blunt cutting shoe, and so particularly if the soils are a little stiffer or they're a little sandy, they can be very easily disturbed. And so when we do lab testing, we quite often underestimate things like OCR and the peak strength. And so quite often when we compare it with the CPT appears to be giving larger values of OCR and larger values of peak strength. And that's primarily because the samples are often not that disturbed, and so the lab data is often influenced by that disturbance. Certainly research where people have obtained very high quality block samples or very high quality thin-walled tube samples, they generally find that the correlations from the CPT tend to work quite well, although those constants are not perfectly constant. They need to be adjusted a little bit. But the numbers I've said typically work reasonably well. And we'll go into that in more detail in subsequent presentations. Now, another question, is the sleeve friction a good indicator of residual soil strength for soft and stiff clays? I'm a big fan of using the sleeve friction as an estimate of residual or remolded strength of fine-grained soils. How well does it work? It actually depends on the cone design, because there are many different cone designs around. And some of the older cone designs, particularly out of Europe, use cones that had subtraction load cells. And these are cones where you have a load cell for the tip, and then behind it is a load cell that measures the load on both the tip and the sleeve. And so you have to subtract the two loads to get the friction sleeve load. And those subtraction cones, although they tend to be a little bit more robust, they tend to be less reliable on sleeve friction because you're having to subtract these two measurements to get the sleeve, and any small zero load shift on each of the load cells makes the sleeve friction less reliable. And so generally I recommend that if you want to use the sleeve friction for better estimates of things like the molded strength of clays, then I recommend using cones that have separate load cells, and make sure you pay very careful attention to the zero load readings, and make sure also you pay careful attention to the tolerance in the standards between the dimension of the tip and the dimension of the sleeve. Most standards require that the sleeve cannot be larger than, the tip cannot be larger than the sleeve, because of course if the tip is larger than the sleeve, then the sleeve ends up being basically in the shadow of the tip and you get much lower sleeve frictions. So the sleeve must be either the same size as the tip, or it can be just slightly larger, but only within a few fractions of a millimeter larger, and the standards specify those tolerance. So as long as you pay careful attention to tolerance, zero load readings, and use cones that have separate load cells, then the sleeve friction tends to be more reliable and therefore tends to give reasonable estimates of sleeve frictions. Now, having said that, some cone manufacturers have designed their cones to produce slightly larger sleeve frictions because they want to avoid measuring very low or negative sleeve frictions. And so often that will show up where if you compare the shear strength from the sleeve with the peak strength from the tip resistance using some cone factor, NKT of about 14 or 15, if the sleeve friction is larger than the peak strength, then that's often a warning that the sleeve measurements may be overestimating the sleeve resistance, because most soils have some slight sensitivity where the remolded strength is a little bit lower than the peak strength. Okay. Well, hopefully that's given you a good introduction to the CPT. As Kelly has said, we'll try to have webinars about every 3 months, and subsequent ones will pick an element of the interpretation or application and go into that in more detail. And hopefully you found this useful. If you do have any additional questions, then feel free to send us an email. We're always happy to respond to questions. And if you go to the Gregg Drilling website, we do have a CPT guide, which is a fairly comprehensive guide that covers everything we've talked about, and you can download that for free, and it'll give you some additional information to read.